Now we're going to shift spheres. We began the course with weather and climate, which are in the atmosphere. Then we shifted to water, which is the hydrosphere. And now we're going to move into the lithosphere, the solid part of the earth in which landforms are created. So physical landscapes form within the lithosphere. Therefore, we have to consider what this lithosphere looks like, how it's composed, and how landforms get created. Well, there's two parts to the lithosphere. There's the outermost part called the crust, the outermost 8 to 80 kilometers of the Earth. It varies in thickness from 8 to 10 kilometers under the ocean, where it's thinnest, to 40 kilometers under the continents, and reaches a maximum thickness in the mountain ranges, like 80 kilometers in the Himalayas, which are the largest mountains on Earth. But the lithosphere includes not only the crust, but also the cooler upper part of the mantle, which is the layer beneath the crust. And so, whereas the mantle is up to 150 kilometers thick and it's thickest under the continents, much of the mantle is actually molten, but the outer or upper part of the mantle is brittle and solid and cool. And so the combination of that outer part of the mantle and the crust we call the lithosphere, the solid part of the Earth. About 3/4 of the crust is composed of two elements, oxygen and silicon. Aluminum is about 8%, iron about 5% of the crust, and then there's three other metallic elements that are present in about 2%, but those elements, calcium, potassium, magnesium, are essential nutrients for plant and animal life. So the weathering of rocks that contain these elements produces soil in which plants can grow, and of course animals consume the plants. So those are important minerals. Here we go. Here's a cutaway of the Earth. It's got various layers, but we're mostly concerned about the crust and the upper part of the mantle because that's the solid part of the Earth in which landforms are created. If you are a geophysicist or a geologist, you want to know much more about the Earth, but we're physical geographers, at least for the purpose of this course, and so we'll confine ourselves to the outer part of the Earth and the rocks that we find there. Rocks are assemblages of minerals, and a mineral is a naturally occurring inorganic compound with distinctive chemical composition, color, luster, and hardness. So if you can take an entire course or courses in mineralogy and you study these properties that characterize the different minerals and allow you to identify them. One of the most common minerals on Earth is quartz, which is composed of silicon dioxide. Remember, silica, and oxygen are the most common elements in the crust, and therefore pretty much the most common mineral is quartz, which is also called silica, which is the major part of sand. Most sand is silica. Two basic groups of rocks, the Felsic Rocks, Fel for feldspar, and Si for silica, consist mostly of quartz and feldspar. And there's another group called the Mafic Rocks, where the Ma is magnesium, and the F is iron, and these are darker, more dense rocks than the Felsic Rocks. So you can take a course in petrology, or several courses in petrology and study rocks, but we only need a fairly basic understanding of rocks to understand how they weather and erode to produce landforms. Three types of rock: igneous rock, which crystallizes from the hot molten magma that reaches the Earth's surface. If it actually emerges from the Earth's surface and cools, it's intrusive rock. Intrusive means it intrudes into the crust and cools, and later is exposed by erosion, for example, granite. Extrusive, like the name implies, is rock that is extruded or emerges from the crust, like volcanic lava, and then cools. And these two types of igneous rock are quite different. The intrusive rock that intrudes into the crust cools fairly slowly over hundreds or thousands of years, giving the crystals that comprise the rock an opportunity to organize themselves. And so these are large, coarse, textured, intrusive igneous rocks like granite or diorite. The extrusive rock that emerges from the earth and cools rapidly tends to be fine textured, so the individual crystals usually can't be seen with the naked eye. For example, lava. It's dense, uniform rock. And some lava will form a shiny obsidian or volcanic glass, quite smooth. An entire body of intrusive igneous rock that cools within the crust is called a pluton, and a batholith is an enormous pluton. So the Canadian Shield consists of batholiths, these large bodies of igneous rock. Second type sedimentary rock is the layered accumulation of sediment, mineral particles, that's derived from the weathering and erosion of the other types of rock. Now, sedimentary strata, layers of rock, cover about 3/4 of the Earth's surface, but it's a relatively thin layer. So actually, only about 5% of the rock in the crust is sedimentary. 95% is the other two types, igneous and metamorphic. But, of course, at the Earth's surface, where we study geography, we encounter mostly sedimentary rock. That's comprised of three types of sediment: the inorganic clastic sediment, mineral sediment. Shale is the most abundant of all sedimentary rocks, and it's composed largely of clay. Then the second type of sediment is inorganic. It's precipitated from a chemical solution. It's called evaporites because the chemicals are dissolved in water, and when the water evaporates, they precipitate. So potash and gypsum are examples of evaporites. And of course, the greatest amount of potash in the world is located out of southern Saskatchewan, which is why we have so many potash mines. Limestone is another evaporite. It gets composed almost entirely of calcium carbonate, and limestone is one of the most common sedimentary rocks on Earth. And finally, the organic sediment, preserved plant and animal tissues. At various times in the geologic past, in ancient tropical climates, there's been a huge amount of biomass, and plant remains have accumulated on a large scale. Thick deposits over large areas, they become buried and compacted by overlying layers of clastic sediment and become hydrocarbons. And of course, we have been extracting these hydrocarbons for about the last 150 years and refining oil and gas and burning coal. And so this layer of hydrocarbon that took millions of years to form is being used relatively rapidly. Here are sedimentary rocks. Now, southern Saskatchewan is underlain by sedimentary rocks, but they're not easy to see because our landscape also is covered in glacial materials. They're relatively recently deposited, covering the sedimentary rocks. And also, we don't have these big canyons like they do elsewhere to expose the sedimentary rock, but you can see it in places like in the Cypress Hills. You can see the formations that underlie Saskatchewan exposed in the valleys of the Cypress Hills in southwestern Saskatchewan. But if you really want to see sedimentary rocks, go to places like the U.S. Southwest, Arizona, Nevada, Eastern California, like these pictures show, these beds, these layers of sedimentary strata that were laid down mostly on the continental shelf of ancient oceans and then uplifted by tectonic activity. And as they were uplifted, the rivers cut down. And in the bottom right hand corner, you can see a bed of sandstone and the bedding of the layered sediment in the sandstone. These geological strata can be traced over long distances. It's called the correlation of the strata. A nice picture of a canyon and these sedimentary rocks exposed. And in the bottom, the little diagram on the left shows the entire geologic column from young rocks on the top to older rocks on the bottom. And every different color is a different geologic formation. But different parts of the geologic column are exposed to different locations, but they can be correlated and traced over long distances. And the third type of rock, metamorphic rock, formed from the metamorphosis or metamorphism of the other two types of rock to form new minerals and rock structures. And the metamorphosis occurs when these other rocks are chemically and physically altered by intense pressure and heat. As the crust forms and moves, then the rocks are subject to these pressures, and where the rock is immersed under the earth, it's exposed to the heat, the geothermal heat, and metamorphosis occurs. For example, slate forms from shale. So slate is the metamorphic form of the sedimentary rock shale. And with further metamorphosis, slate can become schist. The metamorphic equivalent of sandstone and conglomerate is quartzite. Limestone becomes marble. Gneiss forms from igneous and sedimentary rocks that have been in close contact with these intrusive magmas where there is a tremendous amount of heat. And so there is this cycle of rock transformation where one type of rock is transformed into another. And it's driven by two sources of energy. There's the underground heat that's released in the mantle from the radioactive decay of unstable isotopes, and also the force of gravity. You can see the kinds of pressures that are exerted against layers of rock by the overlying rock. And above ground, the source of energy is the sun. So the processes of weathering, erosion, sedimentation that are driven by solar energy and again gravity at the Earth's surface can cause metamorphic rocks and igneous rocks to be transformed into sedimentary rocks. Here is a depiction of that cycle of rock transformation with the two sources of energy, solar at the top, radiogenic at the bottom, and at the top, weathering and erosion and sedimentation cause these igneous rocks to become sedimentary. And then the sedimentary rocks along crustal plate margins can be subducted into the earth where they're subject to heat and pressure and they become metamorphic. The metamorphic rocks in the mantle can evolve into intrusive igneous rocks, and those igneous rocks will weather and decay and be eroded to form sedimentary rocks. And so there is a constant and transformation from one type of rock to another over geologic time. Here is the distribution of rock types in North America. This is the rock that's exposed at the Earth's surface, the rocks you encounter in North America. And you can see it's primarily sedimentary. just like we just discussed. 3/4 of the Earth is covered in sedimentary rocks, although just only to a certain depth. And so actually the core of North America is igneous, and you can see that core exposed on the Canadian Shield. The Canadian Shield in northeastern North America. Primarily igneous, but also metamorphic. And then on the west, the Cordillera, the mountain ranges. The mountains all the way from up in Alaska right down into Mexico. The core of the Cordillera is igneous. There's a bit of metamorphic rock, but the margins of the mountains are sedimentary, like the Rocky Mountains are composed almost completely of sedimentary rocks. Here we go, northern Saskatchewan, the Canadian Shield. The rock is metamorphic and igneous, like this rock in the foreground. And then the same rocks you'll find in southern Saskatchewan, but only as boulders because they were transported by the glacier. The glacier that we'll discuss later in the semester that formed over Canada, moved over the Canadian Shield, and carried igneous and metamorphic rocks and left them in southern Saskatchewan, strewn around as what we call erratics. They're erratics because they don't belong here. They are sitting in glacial debris that was transported from the northern Saskatchewan and left here. So there you go. A crash course in geology, something about the composition of the Earth's crust.